Good morning, students. Let us continue with the fourth session of Chapter 9 Force and Laws of Motion. In today's session, we will discuss some example problems. Example 9.1. A constant force acts on an object of mass 5 kg for a duration of 2 seconds. It increases the object's velocity from 3 meter per second to 7 meter per second. Find the magnitude of the applied force. Now, if the force was applied for a duration of 5 seconds, what would be the final velocity of the object? Solution. First of all, let us examine what is given here. The initial velocity u equal to 3 meter per second, final velocity v equal to 7 meter per second, time duration t equal to 2 seconds, and the mass of the object m equal to 5 kgs are given. If we consider the second law of motion F equal to ma and substitute the value of a equal to v minus u by t, we get the equation F equal to m into v minus u upon t. By substituting the values in this equation, we get F equal to 5 kg into 7 meter per second minus 3 meter per second upon 2 seconds. That equals 10 N, where N represents Newton, which is the unit of force. Now, instead of the given time t equal to 2 seconds, if the force is applied for a duration of 5 seconds, that is t equal to 5 seconds, then the final velocity can be calculated by rewriting the equation above as v equal to u plus ft upon m. On substituting the values of u, f, m and t, we get the final velocity v equal to 13 meter per second. Example 9.2. Which would require a greater force? Accelerating a 2 kg mass at 5 meter per second square or a 4 kg mass at 2 meter per second square? Solution. Here we find two objects. The first object with mass m1 equal to 2 kg and acceleration a1 equal to 5 meter per second square. And the other object of mass m2 equal to 4 kg and acceleration a2 equal to 2 meter per second square. Now to find the force required by each of the objects, we use the equation F equal to ma, that is the second law of motion. The force F1 of the first object equals m1a1 and that equals 2 kg into 5 meter per second square and that is equal to 10 newtons. The force required by the second object F2 equal to m2a2, that is equal to 4 kg into 2 meter per second square, which gives us 8 newton. Since the first force 10 newton is greater than the second force 8 newton, this implies that F1 is greater than F2. This shows accelerating the first object of 2 kg mass at 5 meter per second square would require a greater force. Example 9.3. A motor car is moving with a velocity of 108 km per hour and it takes 4 seconds to stop after the brakes are applied. Calculate the force exerted by the brakes on the motor car if its mass along with the passengers is 1000 kgs. Solution. Here, the initial velocity of the motor car u equal to 108 km per hour is converted into meters per second by taking the value of 1 kilometer as 1000 meters and 1 hour as 60 into 60 seconds. So we get U equal to 108 into 1000 meters upon 60 into 60 seconds, and that equals 30 meters per second. As the brakes are applied, the final velocity of the motor car will be taken as V equal to 0 meters per second. The total mass of the motor car along with its passengers is 1000 kgs, and the time taken to stop the motor car is t equal to 4 seconds. To find the force F applied by the brakes, we use the equation F equal to m into V minus u by t. Substituting the values, we get F equal to 1000 kgs into 0 minus 30 meters per second upon 4 seconds. This equals minus 7500 kg meter per second square, or minus 7500 Newton. Here, the sign is negative as the force exerted by the brakes is opposite to the direction of motion of the motor car. Example 9.4. A force of 5 Newton gives the mass m1 an acceleration of 10 meter per second square, and a mass m2 an acceleration of 20 meter per second square. What acceleration would it give if both the masses were tied together? Solution. Here, first of all, we need to find out the individual masses m1 and m2 of the two objects. Then, the acceleration is to be found out when the total mass is considered. To find out the individual mass, we use the equation F equal to ma, implies m equal to F by A. Therefore, m1 is given by F by A1 and m2 is given by F by A2. Substituting the values of F as 5 Newton and A1 equal to 10 meter per second square and A2 equal to 20 meter per second square, we get m1 equal to 5 Newton by 10 meter per second square, that is equal to 0.50 kg, and m2 equal to 5 Newton by 20 meter per second square, that is equal to 0.25 kg. The total mass m is given by m1 plus m2. Substituting the values of m1 and m2, we get m equal to 0.50 kg plus 0.25 kg, that is equal to 0.75 kgs. With the values of force F and mass m, we can find the acceleration A using the equation A equals F by m. That is equal to 5 Newton by 0.75 kg. That equals 6.67 meter per second square. So, the acceleration is 6.67 meter per second square. Example 9.5. The velocity time graph of a ball of mass 20 grams moving along a straight line on a long table is given in figure. How much force does the table exert on the ball to bring it to rest? Solution. As we can see in the picture, the initial velocity of the ball is 20 centimeter per second, and this is u. But due to the frictional force exerted by the table, the velocity of the ball decreases to v equal to 0 in time t equal to 10 seconds. Since the velocity time graph is a straight line, it is clear that the ball moves with a constant acceleration. The acceleration A is found out using the formula A equal to V minus U by T. Substituting the values of V, U and T, we get A equal to 0 centimeter per second minus 20 centimeter per second upon 10 seconds. Note that force, when the s in the denominator is also shifted to the numerator, it becomes per square. Therefore, A equal to minus 2 centimeter per second square, that is equal to minus 0.02 meter per second square. Now, we can find the force exerted on the ball using the equation F equal to ma. The value of mass m equal to 20 grams is converted into kilograms by dividing 20 by 1000. Therefore, F equal to ma, that is equal to 20 by 1000 kgs into minus 0.02 meter per second square. That is equal to minus 0.0004 Newton. Here, the negative sign means that the frictional force is opposite to the direction of motion of the ball. That's all for today, children. Thank you.